All right, good morning. How y'all doing? Hanging in there?
Yeah, you're doing pretty good.
3 classes left. Let's see how we do. We're going to finish up power series. There were 2 examples that I didn't do last time at the end of class. We had started working on one problem. We had done part A of this note, but I didn't check the endpoints, and I think I left that up to you. So were there any questions on checking the endpoints on that one? What did y'all get? Did y'all get, I know, divergence on one end and convergence on the other, right? Yeah. Audrey, yes, no problem. Do what you gotta do. Okay, so let's do part B then, which is this one here. So what we want to do, instructions here are to find the radius of convergence and then find the interval of convergence for the following power series. So here's our series. And to find the interval of convergence and radius of convergence, we need to do the ratio test on this to see what it does, right? So we're going to run the ratio on this. And for that, I'm going to take the limit as n goes to infinity of the absolute value of, okay, I'm first going to plug in n plus 1 into this. Everywhere I see an n. So this will become 3 to the n plus 1 on the bottom. And then I'm supposed to divide that by the original sequence formula, but I'm going to multiply it by the reciprocal, which has kind of become automatic at this point for me. I'm not writing the ratio. When I have a fraction, I just flip the second one over. And we want that, right, to be less than 1. This is what we want for convergence. All right. The stuff with the n plus 1s, let's kind of rewrite those. Are y'all starting to see like the same sort of like format for all of these, like the same sort of things are happening, cancellation and stuff? All right, so let's see. I'm going to rewrite that x plus 2 to the n times x plus 2 to the first power over. Now on this one on the bottom, I'm going to want the 3 to the n plus 1 to cancel here. So I'm going to write this as 3 to the n plus 1 times 3 to the 1. That way it'll cancel with this one on the top right. Okay, I want that to be less than 1. And we start canceling stuff out. So we've got the x plus 2 to the n goes away. The 3 to the n plus 1 goes away. And so what's left here for me is, let's see, the stuff with x in it, I've got an x plus 2. I'm going to put that over here in parentheses. I need this to be less than 1. And I still have on top an n plus 1. And on the bottom, I have the 3 and the n, so 3n here. And those are being multiplied together. So now we can just take the limit, and over here, the only thing that's impacted by the n is this right here, and that goes to infinity over infinity. So if we run L'Hopital's rule on that, we're going to get 1 over 3, so 1/3 is what we would get. So we need the absolute value of 1/3 times x plus 2 to be less than 1. Any questions up to this point? Are we good? Yes. So to find the radius of convergence, what you need is this. You need to get something that looks like this: x minus a absolute value less than some number r. And that number r will be our radius of convergence. And then to do the interval, we have to break down the absolute value. So right now, I don't quite have that. I have like an x plus 2. I need the 1/3 to be gone here. So I can take the absolute value of 1/3, that's just 1/3. And then multiply both sides by 3. And so here we have the form that we need that matches this. And so my radius of convergence is 3. So R equals 3. I've answered half of what I'm supposed to answer. The radius of convergence is 3. Now I need to find the interval of convergence. So to find the interval of convergence, it's a little more work. We've got to drop the absolute value, make it less than 3, and then make it greater than -3. And then get x in here by itself. So we'll subtract 2 from everything. So when I subtract 2 here, I get -5. Subtract 2 here, I get 1. So I know right now that as long as you give me a number, an x value between -1 and 5, and plug it into this power series, I will have convergence. What I don't know is what happens at the endpoints, right? Right, don't know. So I need to check them. I need to check the endpoints. I'm gonna have to go to the next page to do that. So I'm gonna have to check at -5 and at 1, and I'm gonna be checking this power series. So I'm gonna go to this power series, and we wanna test it at x equals -5, and then we wanna test it at x equals 1. So if I do -5, all I'm going to do is replace every x I see, I replace it with -5. So the series becomes sum n equals 0 to infinity. And okay, if I replace this x with -5, I'm gonna get -3 to the n over, and then on the bottom I have 3 to the n plus 1. Now notice I have a base of 3 on both of these, right? So watch what I do. I'm going to take the one on top and rewrite that as -1 to the n times 3 to the n. That's just properties of exponents that I can split the -3 into -1 times 3 and then break it apart into 2 pieces. And on the bottom, I'm going to rewrite the 3 to the n plus 1 as 3 to the n times 3. The whole purpose of that was to get these to go away. And then from here, clean it up a little bit. This is going to be n times -1 to the n over 3. And that series diverges. I know it diverges because think about the sequence in here, and what is this sequence doing? Well, n is getting huge, right? It's becoming infinitely big, and then it's alternating. So it's alternating between positive and negative numbers that are getting bigger and bigger and bigger. The key is that it's not going to 0. Remember, we need it to go to 0, right? If it goes to something other than 0, which here it's going to something other than 0, right? This right here is not headed to 0. And therefore we get divergence. It's kind of like the nth term test. We know that that thing isn't going to 0. If it went to 0, what if it did go to 0? What would that tell us? If that did go to 0, would it tell us that this series converges? No, it would just tell us we don't know, right? But the fact that it doesn't go to 0 tells us it diverges. Okay, now I need to test it at x equals 1. So if I do that, I get n. Okay, if I plug in 1 here, I get 3 to the n. So 3 to the n over, and then on the bottom, 3 to the n plus 1 can be rewritten as 3 to the n times 3. And again, the 3 to the n's cancel. And so all you get is sum n equals 0 to infinity of n over 3. And that again diverges because this just blows up, right? This becomes infinite. This does not go to 0. This, right, does not head to 0, so it diverges. So I do not want to include my endpoints, right? I do not want my endpoints. So the interval of convergence, IC, is going to be everything between -5 and 1, with parentheses on those because I don't want to include them. Or you could write it this way: strictly bigger than -5, strictly smaller than 1. You have to test your endpoints for interval of convergence. For radius of convergence, do you have to test endpoints? No. Interval of convergence, you must. Right, so just be careful with that. If you're asked on a problem on the final to find the radius of convergence, that's less work than interval of convergences, right? Okay, we have one more. All right, this problem, I like to give this problem because it has this weird thing happening in it where it's this pattern, this repeated product thing. So
that happened a couple of times in the 8-4 homework.
yeah, it's in the homework, yeah. So I'm going to do the ratio test here to figure out what's going on. So I'm going to take the limit as n goes to infinity of, okay, I've got to replace everything here with n plus 1. So n plus 1 squared times x to the n plus 1 over, now how am I going to write this? 2 times 4 times 6 times 8 times dot, dot, dot. But I'm going to stop at 2 times n plus 1. So I'm actually going to be stopping at 2 times n plus 1. And just get into a habit of this. The one right before this is good to write down. The one right before this would be 2n. The way to see that would be 2n is to see that this one is really 2n plus 2 when you distribute the 2 through. And notice these jump up by 2 each time, right? They're going
Professor,
up by 2. So
I'm
if we go from right to left, they go down by 2. What's that?
I'm a little bit confused. That's not a factorial because it's not multiplying down, right? It's just multiplying exponentially up by n.
Yes, n is going to infinity, right? So the n's getting bigger as opposed to a factorial that's just, well, this is kind of a factorial, but factorials, they go, the increment on a factorial is by 1 each time, right? Right, so like n factorial is n, and then you subtract 1, and then you subtract another 1, and then you subtract another 1. This one, whatever it is, we're going down, but we're going down by 2 each time, right? Okay, so what I was saying is that if the last one is 2 times n plus 1, then if we distribute the 2, you get 2n plus 2. The one in front of it should just be 2n because it should be 2 less than this one, right? From right to left, it goes down by 2 each time. So if I subtract 2 from this, I get the 2n. That's important because it's going to help cancel when I rewrite this flipped over. This numerator up here is going to have that 2n in it. So I like to identify it now. So I'm going to take that and
Everything but the 2n plus 2 going to cancel on there?
everything, yep, all of these are going to go away. So this stops at 2n here. And then on the bottom of it is the n squared x to the n. We need all of that to be, we want all of that to be less than 1 for convergence. So let me save myself some trouble here. This is x to the n times x. And now let me cancel stuff. 2, 2, 4, 4, 6, 6, 8, 8. Everything in the dot dot all the way to the 2n will cancel. So that's why it's important to see that 2n. This one here in yellow doesn't get canceled with anything. This doesn't get canceled. This doesn't get canceled. The x to the n does get canceled. So in terms of what I have left, I have, in terms of x, I just have that x. So I'm gonna put that x here. And then everything in yellow I still have. So I have, let's see, n plus 1 squared on top. Then I have on the bottom, I'll write it this way, n squared times 2n plus 2. Multiplying. And then I want to let n go to infinity, right? I want to let n go to infinity. So if I let n go to infinity now, I get infinity over infinity. So I've got to somehow do some L'Hopital, but what I think would be easiest before L'Hopital is to just expand that. That's n squared plus 2n plus 1. And on the bottom, distribute the n squared through, you get 2n cubed plus 2n squared, and then times x less than 1. And now this is just a little easier to do L'Hopital on. The derivative is, you don't have to do product rule and chain rule, just, nice derivatives. So the first time we do L'Hopital, this becomes 2n plus 2, and then the first time here becomes 6n squared plus 4n. Understand, that's when I do L'Hopital once. And I still have infinity over infinity. So I do L'Hopital again. This is 2. This is 12n plus 4. So this right here is L'Hopital twice, right? So we get limit, n goes to infinity. All that's left there was 2 on top, 12n plus 4 times x. I need that to be less than 1. But this guy goes to 0, right? Fixed number on top, bottom goes to infinity, that goes to 0. The absolute value of 0 times x, I need that to be less than 1. This is true always, right? Fix me an x, give me an x, doesn't matter what it is. I'm going to multiply times a number that's going to 0. That is definitely going to be less than 1. And remember, you're not allowed to give me infinity for x. X has to be a fixed real number. So this is true all the time, which means that any x works. So your radius of convergence and interval of convergence don't require any work. We'll start with the interval because I think the interval is easier to understand. The interval is just everything. Okay, any number will work. The radius is how far out you can go in each direction. So that's going to be infinity as well.
Professor, as a quick question in terms of notation, we could have done 1 plus 1 divided by n all squared times 1 over 2n plus 1.
You could have done 1 plus 1 over n, all of that squared times 1 over 2n plus.
Yes,
2.
and then we
Yes.
just shoot L'Hopital. Okay.
Yeah, you could have done that.
I have a quick question because I bumped into it in the homework and it was a far more messy thing to multiply it all out. But it
Mhm.
was one of those where the analysis of it ended up with me ending up with an into like the 4th on top and an into the 5th on bottom.
Yeah.
Being my highest powers, where is it reasonable to say I can look at this and tell I'm going to end up with a number, an infinity to a higher power on bottom. So when I grind it away with L'Hopitals, I will end up with infinity on bottom and a constant on top, right?
Absolutely.
Is that
If
a
they're-
reasonable?
if they're polynomials, as long as
Yes.
they're just polynomials, then if the degree of the denominator is higher than the numerator, then it's going to go to 0.
Okay. And vice versa if it's on top is higher.
If at the top is higher and the bottom's
Then-
lower, then it's going to go to infinity. And if they're the same, it turns out to be the leading coefficients.
Yes. Yeah,
Yeah.
no, it's been a minute since I did limits.
In college algebra, when you're taught about the horizontal asymptotes of rational functions, you're taught, it just depends on who teaches it, but if you haven't seen the limit, you're taught, oh, if the degree of the numerator is smaller than the denominator, the horizontal asymptote is 0, which is basically what you're saying right now. And if the degree of the top is bigger than the bottom, then it doesn't have any horizontal asymptotes, which means it takes off to infinity or negative infinity at the ends. And if the powers are the same, then you just look at the leading coefficient of the numerator and divide it by the leading coefficient of the denominator. That's exactly what would happen when you did L'Hopital's rule. So they kind of just give you the end result in college algebra. They don't tell you exactly like why. Unless you talk about the limit in college algebra. Sometimes professors will talk about the limit, but it's kind of weird to talk about the limit in college algebra because you haven't really done any limits, right? All right, so that's it. That's power series. I guess the main takeaway is that power series is a series that involves a variable, right? The convergence or divergence of a power series would then depend on the value of x we're plugging in. And for the values of x that work and make it converge, we can define a function to be that power series. And then the interval of convergence would basically be the domain of that function. That's, that's kind of the big takeaway. So now we move on to the next section.
Real fast, what should be doing for the homework for 8.5? Just in all of it now?
Yeah, just try it all.
Gotcha.
Yeah.
I gotta say that ratio test.
It's
Nice.
yeah, it's pretty nice.
Yeah, going from the 8.3 homework where you're having to just try and figure them out, and then you go to the 8.4 homework where it's like, oh, they're mostly ratio tests with some odd outliers, and then this, it's like just a ratio.
Yeah, so the ratio test is really good when you have x to powers, because that power n becomes an n+1, and then you can always break it apart and cancel. That's why the ratio test is so great with power series, because you have the exponent that gets the n+1 on it. So you'll always get the cancellation to happen. And it turns out that power series are all we need. Fortunately, there's not other series that we need to represent functions. So it all just kind of works out. Okay, so we're moving on now. You know what a power series is in terms of just generic, what's a power series. Now we start our first, we dip our toes into the pond here. We want to know, is there a way that I can start with a function and turn it into a power series, right? Can I start with a function, turn it into a power series? What we're going to do right here today is very limited. Like I'm not giving you a full blown, like, this is the way we do it. This is just, hey, for this example, notice we can do it. So for very specific scenarios, there's ways to turn functions into power series. A general way of doing it is the next section, all right? So here's where we are. Now let me make this a little bigger. So we know what a power series is, okay? We now attempt to take some known functions and see how to write them as power series. So we're going to start with something familiar. This is from last class. We already saw last class, note 8.5.5, that as long as the absolute value of x is less than 1, then this power series, 1 plus x squared plus x cubed, is like a geometric series that this will converge, right? That this is a convergent series so long as the absolute value of x is less than 1. And we also know that, what does this add up to be? What is another way we can represent this function as long as the absolute value of x is less than 1? What function is this? There's a very nice clean function without a series written. Remember a over 1 minus r? What would it be here for us? What is it? 1 over 1 minus x. Remember that from last class? Very important you remember that, okay? That's a big deal here. In fact, I'm gonna go into my notes. I'm gonna write this down because I want you to really understand it. Okay, what we've seen from last class is that, and I'm going to do it more generally, if the absolute value of u is less than 1, then 1 plus u plus u squared plus u cubed forever and ever is equal to 1 over 1 minus u. All right. Another way you could say this is that the sum n equals 0 to infinity of u to the n equals 1 over 1 minus u. Those are two equivalent statements. The first one, I'm actually writing it out, 1 plus u squared. Here, I'm actually just writing the left side as a summation. This all relies on the fact that the absolute value of u is less than 1. So I'm using that generic formula now with u instead of x, okay? Big deal, it's a dummy variable, who cares? All right, let's make sure we understand that. All right, so here's our first example. I want us to rewrite this as a power series, and then I want us to express the interval of convergence for this. So this is a function, right? We could look at this as a function, you know, f of x equals 1 over 1 plus x squared. And what I'd like to know is there a way that we can rewrite this as a power series and then figure out what its interval of convergence is? You with me? Well, this looks a lot like, right? It looks kind of, well, I don't know, not really, but if you squint your eyes, it kind of looks like it's kind of 1 over 1 minus u. It kind of is. You'd have to do something. We would have to rewrite it this way: 1 over 1 minus negative x squared. Do you agree that that's the same thing? That's the same as 1 over 1 plus x squared. And then if I do that, I could say this in here is like my u, right? So this should be equal to the sum as n equals, sum n equals 0 to infinity of, what was the formula? I just wrote it down. This 1 over 1 minus u will be equal to, I'll do this one. 1 over 1 minus u is equal to the sum n equals 0 to infinity of just u to the n, right? U to the n. So for us, u is actually negative x squared to the n. Now, this is true, right? This is true only if what? The absolute value of u is less than 1, right? So this is only true if the absolute value of what is less than 1?
Negative x squared.
Negative x squared. And I don't need the negative anymore, right? In fact, I don't need the absolute value at all, because if I take the absolute value of a negative number, it's positive, and any number squared is going to be, what do you call it? Positive, right? So this is really saying x squared must be less than 1. Which means that, well, what does that mean? X must be between 1 and negative 1. Right? Because if I take any number and square it and I need it to be less than 1, even if it starts out negative, as long as I'm between 0 and 1, I should be okay. So this would be my interval of convergence. As long as I'm between negative 1 and 1. Now, what about the endpoints? Do I have to check the endpoints? No. Why? Because this formula only works, okay, right? This formula only works if we are strictly less than 1. We know that because it's a geometric series, like that's where it came from, is the idea of a geometric series. And so if it is 1, then you get divergence. So you don't have to check the endpoints if we're going to use this formula, right? If we're going to use this ever, you don't have to check endpoints. Okay, let me continue here. I want to continue and just write down what this is. Let's just write this sum out. If n is 0, we get 1, right? Now let's plug in 1 for n. So I'm going to say plus, what happens if I plug in 1 for n? I get negative x squared to the first power. Now let's plug in 2. So if I do that, I'll get negative x squared to the second power. Then I plug in 3, negative x squared to the third power. Plus, let's do one more, negative x squared to the fourth power, plus dot, dot, dot. All right, let's do this. This is 1. Okay, if I take negative x squared and raise it to the first power, I just get negative x squared. What happens if you take negative x squared and square it? Negative becomes positive, right? X squared becomes x to the fourth. So this will be plus x to the fourth. And then the next one, I'm taking a negative and I'm cubing it, so it'll stay negative, right? And then x squared cubed, you multiply those, so this will be x to the 6th. The next one will be a positive because we're taking a negative, raising it to the 4th. And so we'll get plus x and multiply 2 times 4 is 8. Plus dot, dot, dot. So I was supposed to express this as a power series. I did that, and I actually expressed it in 2 different ways. I first expressed it here, right, as a power series in the sigma notation. And then I expressed it a second time as a written out first few terms. You should be comfortable with going back and forth between the two, because sometimes it's easier to work with this form. Sometimes it's easier to work with this form. It just depends on what we're trying to do. Okay, so I have expressed this as a power series, and I have found the interval of convergence right here. So what are we saying? What are we saying? We're saying that at the end of the day here, what we're saying is this. If you take the expression 1 over 1 plus x squared, okay, that was the original problem, that you could, if you want to, write that as 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th plus dot, 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 if the x that you're plugging in is between -1 and 1, right? That's what we're saying, is that those two are equivalent. So let's see if this is actually true, all right? Let's see if it's actually true. What I'd like for us to do is let's try x equals a half, and you'll need a calculator for this. If I plug in 1 over 1 plus 1/2 squared, let's do that on the left side. This is 1 over 1 plus 1/4. And 1 plus 1/4 is 5/4, so 1 over 5/4. And that's the same as 4/5, right? And 4/5 is 0.8. Agreed? What we've said is that 0.8, okay, plugging in half, 0.8 is the same. You get that same result if you plugged a half into this side. So if I do 1 minus 1/2 squared plus 1/2 to the 4th minus 1/2 to the 6th plus 1/2 to the 8th, if I did that forever and ever, what would this be getting closer to?
0.5.
Point what?
0.8.
0.5.
0.5 is what we're plugging in.
Oh, 0.8. Sorry.
0.8, right? So it should get closer to 0.8. So I'm going to do this on my calculator. I'm going to actually add just these first ones up. So I'm going to do 1. I'm going to subtract 1/4. I'm going to add, what is that? 1/16. I'm going to subtract 6. I'm going to add 1/2. to the 8th. Look what I get. I actually got, just out of these first ones, I got 0.80078,125. That's what I got. It's close to 0.8, right? I have to go out further if I want to get closer. But if I could go forever, then it would converge to 0.8. Closer, closer.
What's funny is I tacked in the next one because the next one is minus x to the 10th. And it actually went to 0.799.
Yeah, so
It's because it's
actually
jumping up and down over the.
Yep, it's going back and forth. If you look at it this way, almost like a sequence. If this is 0.8, if this is 0.8, what's happening here is that the further we go out, it's like it's doing this. It's getting closer and closer, above and below. This would be if we were looking at the partial sums. S sub n is the partial sum. So if you summed out 1, 2, 3, 4, 5, the first 5 terms, maybe you're right here, you're a little above it. But then, like you said, you went out to the 6th one, and now you're a little below it. And then you go to the 7th one, 8th one, and it's converging. It's headed towards that 0.8.
So, question, is there, how far out should we
It's
go?
pretty far out, man. I know it's far out. What?
No. How far out should we go? Like
Well,
with
depends on what you're doing. Like in this class, I would tell you how far I want you to go out if I was asking you to approximate something.
okay.
We're gonna do that. I think today we'll have an opportunity to actually see, like, okay, how far out are we gonna go, right?
Okay.
Yeah.
So would the standard be like in a more real world situation of you're doing something off the wall and you have to do this, it would probably be to precision of your instruments.
That's right. It'd be the
Okay.
precision of the instruments,
Okay.
which in the real world, I mean, you
It's
can
not
only
going to
get
be
so
super precise.
right?
Yeah.
Right. We can
Yeah.
only get so precise. So that's why people have a problem with the fact that series are infinite, but so you can never really use them because they're infinite, so you can't really go forever. But in the real world application, you don't need to. You
Yeah.
only need to go as far as like you can, is your precision on your, you know, what if you're building something, right? I always think about, like, if I'm building a tricycle out of plastic, you know, one of those little kids' Tykes toys, you know, I don't have to be very precise about that wheel, right? Like I've got a lot of plus or minus on the tolerances when I build a plastic wheel for a little toy. If I'm building an aircraft bearing, right, that's different, right? Something that's going to be spinning at very high speeds, very high temperature. I have to be super precise with that. So that's okay. I mean, the series is infinite. I can go out as far as I need to go to get that accuracy.
Like
Or precision, I should say.
like a rover, right, sir?
I'm sorry?
Like a rover. One of my teachers explained it that if you don't go out this many decimals out, you mean by like a mile. And when you're out in space, that mile is all that takes to mess it up.
Oh, yeah. Yeah, I mean, you have to understand how error compounds though, right? So if you have small error in one place, that could have dramatic impacts on error somewhere else. I don't know if I told y'all, when I was in college, I took a math class called numerical analysis. Did I tell you about the black box thing? No. I'll tell you.
Is that like numerical methods?
Yeah, it's like numerical methods. Exactly. It's how we use computers and technology to solve mathematical problems, right? So in this class, the project, the end of semester project, was that what we had to do is we had to pick 2 programs that are used by engineers, mathematicians, scientists, 2 programs. And what we had to do is we had to come up for each of the programs, we had to come up with a problem. Okay, so I had to come up with some problem that I wanted the computer to solve mathematically. Okay, this problem, whatever I came up with, I had to be able to solve it. Okay, I need to be able to solve that theoretically. Theoretically means by hand. Okay, so like I could solve it. I knew the solution. I could prove to you what the solution was. All right. And then what I would do is I would feed that into that program, and I would have to make it come up with a false result, basically an incorrect answer. So that was the project. I had to do that for 2 programs, pick a problem, show the solution theoretically, feed that problem to the computer, and have the computer give me an incorrect result, which meant that I had to understand the code, right? I had to understand the code that was being implemented for the problem. And this black box idea is like, as an engineer, you're going to use software, okay? You're going to, and it's going to be a black box. You're going to plug in the thing and you're going to trust that result. You're going to trust it, right? Somebody still has to understand the code, and they need to understand the mathematics, because there are weaknesses in code, right? And you can exploit the weaknesses. So that's basically what this project was, is exploit the weakness of the code. So I'd have to understand the code. And a lot of that, Brandon walked away. I mean, this had to do with what Brandon was saying. A lot of this exploitation of the code was to see how it dealt with rounding things, and then to make it compound that error somehow, and then make it give me a false result. And so, or not false, give me an answer that's wrong, is basically what I'm saying. So this was a very interesting, semester project to do. Anyway, okay, back to.
Oh, wait,
That sounds like fun.
what'd you put into it?
I don't remember. I think it was a system of nonlinear differential equations that you can have a
That'll do.
computer solve differential equations, and then you can have a computer solve linear differential equations, then you can have a computer solve nonlinear differential equations. And I believe I fed it something, and it basically made the code go nuts, and it gave me an answer, just wasn't right.
Yeah.
And it was easy to show the solution. It was very easy to show the solution theoretically, but
Yeah.
Okay. So, I mean, I guess the point of this is what I said earlier, and that is, or a minute ago, which is, as much as we want to trust our technology and trust the answers coming out, you still have to have people who are trained in the theory, right? Like, why would I ever need to learn how to do derivatives and use limits? Why, if I can use a computer to go do that for me, right? Well, we still have to have the branch of mathematics. We still have to have mathematicians who can theoretically prove things. And then we need computer scientists who understand code and how the rounding works and error and all that. We can't just give it up and just be like, yeah, throw it into the black box, trust the answer, right? Okay. Where were we?
That's how people
Okay.
die.
Yeah, this is where we were, right? So this would work. Now, I'm going to give you a little preview as to why, why would you ever, I told you this, why would you ever want to replace this, which is a very clean expression, right? This is very nice, 1/1 plus x squared. It was easy to plug in a half and get the answer 0.8. And it didn't require a series to do that, right? It did not require a series to do that. So the reason why I'd want to do that is, what if I asked you now to integrate that function, find the antiderivative? Well, you could easily do that because that's arctan. Do you all recognize the antiderivative? That's arctangent. But if it were something more complicated, it would be much easier for me to integrate the series, because this is super easy to integrate, super easy. All right. Even differentiate. If you ask me to differentiate this, I'd have to do quotient rule or something, or bring it up as a negative power. I can just differentiate this, and it's much easier. And again, how accurate do you need me to be? Sure, fine. I'll go out as far as I need to go. All right, let's keep going. All right, so that was our first example. This is the old notes. What the hell? Yeah, we did this already. Next example. Hey, where'd the little thing go? find a power series representation for this function. All we have right now in this section, all we have is this. 1 plus u squared plus u cubed plus ... is equal to 1 over 1 minus u, so long as the absolute value of u is less than 1. That's all we have to work with. So let me show you. What I'm going to do is this. I'm going to rewrite this as x to the 4th times 1 over. I'm going to switch the 5 and the x on the bottom, x plus 5, make it 5 plus x. You okay with that? Do y'all agree that that's the same expression? All right, now I'm going to do this. Okay, what I did here is I noticed that, see, in my formula, I have to have a 1 down here on the bottom. You see that 1 minus u? And so I have a 5 here. I'm going to turn it into a 1. And so to turn into 1, I have to factor a 5 from both of these. And there's no 5 to factor here, so that's why I had to put the 1/5 here. And now this is x to the 4th times 1/5 times, now I'm going to, I'm basically massaging this thing into what I want it to be. All right, there we go. So I've turned the 1 over 1 plus 1/5 x into 1 over 1 minus negative 1/5 x. And now it looks exactly like I want it. It's 1 over 1 minus u, right? But u for us is actually this, right? That right there is the u.
So what do we do about that x to the 4th
Yeah,
times 1/5?
Yeah, what do we do with it? Well, let me keep going. Okay, so this is equal to x to the 4th. Let me do it this way. 1/5 times x to the 4th. We normally would write the 1/5 in front of there. Times, now this turns into a sum, n equals 0 to infinity of negative 1/5 x to the n power if the absolute value of what's less than 1. So long as what? I can do this step. I can go from here to here as long as the absolute value of what's less than 1 here.
So
I'm a
negative
little bit
1/5 x.
Negative 1/5 x.
Sorry, I'm a little bit confused.
The u.
Why did we take that out of our summation?
Why do we take what out of the summation?
1/5 x to the 4th.
I didn't take anything out of any summation. What I did was I'm taking my original expression, x to the
What you
4th,
know, and then you're gonna add it on to. Oh, okay, my bad.
right? I'm taking this and then I'm just algebraically kind of like pulling things apart. This is equivalent, right? These two lines are equivalent. Those are the same things, right? That's the way fractions work, right? I could just slide that x to the 4th up top. I pulled it out. I'm trying to make it look like 1 over 1 minus something, 1 over 1 minus something. I have 1 over 5 plus something. So I pulled out a 5. Pull that 5 out on the bottom. Now I have 1 over 1 plus something. I'm getting closer. I need it to be 1 over 1 minus something. So I rewrote plus 1/5 x is negative or minus negative 1/5 x. So I'm not pulling this out of a summation because I haven't even done a summation yet. My next step is when I'm converting this in yellow to its series under this condition. And that ties into that up there, right? We still have this sitting out here, okay? I'm not done with this. Before I continue though, I just want to clear up over here what our interval of convergence is. This right here, I can take the absolute value of the negative 1/5 and get this. I can multiply both sides by 5. And then I can drop the absolute value and have my interval of convergence. So I am allowed to do this. Everything that I've done here, everything I've done is valid so long as I'm talking about values of X that are between -5 and 5. As long as I'm doing that, then what I'm doing is okay. May I continue?
Would that be it for this problem
Nope.
or no?
Nope, we're not done. We have
Okay.
to deal with this 1/5 X to the 4th.
Oh, yeah.
Okay, so now watch. Let's do it this way. Let's do this. How about I do -1 to the n, 1/5 to the n, x to the n. All I did there is I pulled everything in here apart. Negative, that's a -1, that's a 1/5, that's an x. They're all being multiplied together, so they're all to the n power. So I just ripped it all completely apart. And the reason I did that, and I want you all to really think about this, all right? This right here is a sum, right? So it's something plus something plus something plus something, right? And it keeps going forever, yes? And I have a 1/5 x to the 4th that would distribute through to each one of those, wouldn't it? So what I am allowed to do with this is push that 1/5 x to the 4th inside the sum, because it's going to, this 1/5 x to the 4th is going to hit every single one of these, right? Every single one of these gets it. So I'm going to rewrite what's up here. But I brought that 1/5 in with the x to the 4th. And now you can start combining some of this together. Like, for example, I have a 1/5 to the n and a 1/5 together, right? Those two would become a 1/5 to the n plus 1. So I have -1 to the n out here. I have a 1/5 to the n plus 1. And then x to what power?
N plus 4.
N plus 4. This is your power series.
So you're allowed to just plug it in
Plug in, what do you mean plug in?
in terms of that x to the 4th and that
You're allowed to multiply it into the series, and which means it just gets tacked into the formula. So that's my answer. That's the power series. Now, what I'd like to do is write out the first few terms. So I'm going to let n be 0, then 1, then 2, then 3. We'll probably write 4 terms out. So if I let n be 0, let me work through this. -1 to the 0 is +1. 1/5 to the 0 plus 1, that would just be 1/5. And then x to the what? I'm plugging in 0, right? So x to the 4th. Now I'm going to let n be 1. So if n is 1, I get a negative now. So minus, and then I'm going to have 1/5 to what power?
The second.
Second, 1/5 squared is 1/25. And then x to the, let's see, where are we? I'm plugging in 1, right? So 1 plus 4 is 5, so x to the 5th. Now I plug in 2. When I plug in 2 for n, I get -1 squared, right? Which is going to be a positive. Now I have 1/5 cubed, which is 1 over 125. And then x to the what? I'm plugging in 2, right? 6, right? And then the next one will be minus, right? Dot, dot, dot. It keeps going. I won't do the next one. Well, I guess so. What is it? It's a negative, right? 1 over what? You just have another 5 down there, right? So 625?
Yeah.
X to the 7 plus dot, dot, dot. I'm going to show you something I probably shouldn't. All right, I'm gonna show you something I probably shouldn't. Should I do it? Yeah, I'm gonna do it. Okay, I'm at Wolfram alpha. What was our original function? X to the fourth over
X plus 5.
X plus 5. Just type that into Wolfram alpha. Let's see what happens. It's probably going to give me a graph. Alternate form. Here's an alternate form. Let's go down here. Series expansion. There we go. Series expansion. That's our answer, yes? Now they went out more than we did, and it took them less time. Right? So we got these, and then you see this OX ninth power, it's just saying it's stopping at the ninth power of X. Like there's more to this, but it's stopping here. And I think you can actually ask it for more. No, it won't let you have more. Big O notation. Oh, is that? Oh, that's just a reference. Sorry. Okay.
I forgot Big O. Big O was stop or was it infinite notation?
What?
For computers, it was Big O is like stop summation here, or was it continue function till? But like there's more, but we just stopped it.
It depends on what you're talking about. Here, okay. This one, let me see what they're referring to here. Yeah, this is not what I'm looking for. Big O is in computer science is like operation count, like whether or not it's linear, logarithmic, quadratic, something like that. Is that what you're referring to? Here, this Big O, they're just telling you that they're stopping here at the ninth power. They're not including the ninth power and on. Like this series goes forever, right? The series goes forever. Do you see where it says expansion at X equals 0? See that? Do you remember when we were talking about where a series is centered? It's centered at 0 here because look at our formula had just X, right? It wasn't X minus 2 or X plus 1 in parentheses to the n. That's why it's centered at 0. All right, I'm moving on. All right, so the whole point of this, or not the whole point, but a very big aspect of this is being able to differentiate and integrate power series. So we're right now, we're just figuring out how we can express certain functions as power series. So if the radius of convergence is bigger than 0, this is important. So it's saying, look, let's say we have a function that at least has some interval where it's defined. If the radius convergence was 0, then that was that real crappy situation where you only have a single point and it's a useless function. So as long as the radius convergence is bigger than 0, that means we have some interval of convergence. And then this function would be well defined, meaning that it would have some meaning to it. On some interval, it would have meaning. It'd be meaningful. We would like to be able to differentiate it and integrate it. So I'm going to take this. I will show you the formulas in a second, but I want us to figure out the formulas on our own. I mean, with each other first. Okay, so let's say this is a generic power series right here. Okay, there's a generic power series, and I would like to know what the derivative of this is. Assuming that this is defined and that the function exists on some interval. If I ask you for the derivative of this, let's start going here. So how about this first term, c sub 0? That's a constant, right? Derivative constant is 0. Plus, now we have a constant in front of x minus a. Let me give you an example of what that would look like in like some other scenario. 4 times x minus 3. If I asked you to take the derivative of this, right? You would just bring the 4 down for the ride, and just derivative of x minus 3 would just be 1, right? So all you get here would be C1, the constant that's out front. Plus, now let's do the second one. An example of this would be something like 4 times x minus 3 squared. If I asked you to take derivative of this, you would ignore the 4, right? It's going to come for the ride. You'd bring the 2 out in front, right? So the 2 would come out, and then it would be this to the first power times the derivative of what's inside, which is 1 again. In other words, the 2 is going to come out, hit the c sub 2, and then you're still going to have the x minus a to the first power. What about the next one? Comes out, 3 c sub 3, this time x minus a squared. And then we just keep doing this, right? Just all the way down. Plus 4 c sub 4, x minus a, this time to the third, plus dot, 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 forever. That okay? Can you help me rewrite this in sigma notation? So you can ignore this. You don't need that. What do all of these have? All of them, let's start with the x minus a. This is x minus a to the first, x minus a squared, x minus a cubed, right?
N minus 1.
And minus, okay, so where do you want to start your index at? You want to start it at 1?
Yes.
Okay, and so then you're going to have here an x minus a to the n minus 1. Do you all agree? Look at this, because there is sitting in front of this, or sitting next to this would be an x minus a to the 0, wouldn't there be?
Yeah, I agree. That looks right to me.
Okay,
And
then
then you
what
have
goes
your
in front of
constant.
each? What goes in front of this then?
Your constant.
C to the n.
The constant?
C sub n.
C sub n. And what goes in front of the c sub n?
The
N.
The
Yeah.
n that
N.
we're at, the n that we're at, right? N like this.
This is
Do y'all
the
agree this
derivative
formula
formula.
would do it? This formula would do it, right? If n equals 1, I get 1 times c sub 1, x minus a to the 0, which would be this. If n is 2, I get 2 c sub 2, x minus a to the first. That's this one. If n is 3, I get 3 c sub 3, x minus a squared. That's this one. This formula works, right? You understand? Yes? But look, check this out. This is actually pretty cool. If you take what we started with, right? Aren't you really just doing the power rule? Look, aren't you just bringing this n out front?
So you can do the power rule to summation.
Hold on, right? It's almost like we just brought the n out front, right? It's almost that's all we did, like what we did back in Cal 1 in the beginning.
We also did shift our starting point up 1.
We did shift it though. We did start at 1 though, instead of at 0. But that's what this is, right? So differentiating a power series is what you think it would be. It's just bring this n out front, subtract 1 from the n, and shift your index up to 1. Now, if I wrote 0, would it be wrong? If I did forget to shift it and I did this, would this be wrong? No, because if n is 0, what? This is all gone, right? So you don't get a first term. So
I
it's
mean,
not
it would
incorrect.
just be that first term that we got rid of because it was 0.
Yeah, this right here, it actually generates this guy right here, which you don't need.
Yeah.
Okay, so let me go to my notes. This theorem, it says, make this bigger for you. It says, if you have if you have some function that's a power series that's defined on some interval, okay, then the derivative of it, we just worked out, is this sum right there. And notice I did shift the index, I went to 1. Okay. All right, now, what about integration? So what if we take this and we want to integrate this, right? So what would the antiderivative of this function be? Well, okay. Before we do anything, when you do any antiderivative, don't you have a constant? Plus c, isn't there a plus c on every integral? You always do whatever the antiderivative is plus c. Well, my answer goes forever, right? This is going to be an infinite series, so I can't put a plus c at the end. So I'm going to put the plus c in the front, right? So I'm just going to have some constant, okay, plus, now let me start with the antiderivative. What's the antiderivative of this? Well, it should just be that times c sub 0 times x, right? So I'm thinking about it like this, like if this was just the number 4, the antiderivative would be 4x. And then here, let's say an example of this, if this was 4 times x minus, let's say 3, the antiderivative of that, you would leave the 4, you would be looking at the antiderivative of this, which would just be 1/2 x minus 3 squared. That would be the anti. That would be the integral of this. So this is going to be plus 1/2 c sub 1 x minus a squared. And then the same thing's going to happen on each one of these. You're going to add 1 to the power and then divide through by that power. So plus 1/3 c sub 2 x minus a cubed. Go to the next one, 1/4 c sub 3 x minus a to the 4th, so on and so forth. Which is just what you would, again, hope if I asked you to find the antiderivative of that right there. You're going to add 1 to n here, but you've got to divide through it as well. Divide through by that. 1/n plus 1 times c sub n x minus a to the n plus 1, and n will still start at 0 here. There's no shifting of the index when you do an integral. Y'all see that this works? If n is 0, you get 1 c sub 0 x minus a to the 1, which is this. Y'all are just going to take that? Y'all aren't going to challenge me on that at all? If n is
Sounds
0,
reasonable.
if n is 0, this is right. Just tell me what happens when n is 0 on this formula I just put up here. If n is 0, you get 1/1 times c sub 0 times x minus a to the 1, right?
Is this proof to integration, or is this more of like, because n's are variables, we can still integrate them?
No, this isn't a proof of integration. This is just, how does integration work on series? Like, what is it that happens when you try and integrate a series?
Where n is still a variable and it still acts as a function because we made it that way, and then we could still integrate it.
N is not a variable in the sense that x is a variable. X is a variable, n is our index that counts from 0 to infinity. I mean, it's
So
variable in the
indexes
sense that it's
are-
changing, but it's not like the variable in the sense that x is the input for the function. Those are two
So-
separate ideas.
Do they fundamentally move the same?
No.
That's the
n
only
is-
way it would
n-
integrate.
N is only 0, 1, 2, 3, 4, 5. X is some real number. N's have to be positive integers and they have to count specifically 0, 1, 2, 3, 4. So that's a different type of variable than X. X here has to be a number somewhere in the domain of the F, which is in the interval of convergence.
Is my confusion valid? Sorry, I'm I'm kind of confused because I'm looking at n as kind of like a variable, right? But it's working like a variable, but it's not. Do they have some rules that apply?
Define variable to me.
Variable is an input to a function.
Okay. There's only one function here, and that's the function f. And that function f takes in an input x, right? We are defining the function to be this series of things. The only way that I can represent that function to you is by using this notation called sigma notation, where I use a secondary variable n to actually represent me counting out forever. Those are two different concepts though. The x is the input to the function. The n is just helping me represent this infinite string of things in a way that you can understand it. Yeah, we'll have to pick up that conversation elsewhere, because I mean, we have to understand, I guess, or you have to understand, how are we going to define what a variable is in your mind? I need to understand how you're thinking of a variable as opposed to what a variable means in this context. Because I mean, anything that changes, you can say is variable, right? It varies, right? N does vary here, but it's not the same type of variable as x is in this situation.
Yeah, mathematical variable versus a programming variable.
So there's different types of variables. This one being a different type, however, we can still integrate it. Closing out.
Say it one more time.
Sorry about that. Different types of variables. However, we can integrate this different type of variable.
It doesn't make sense to me. The statement doesn't make sense to me.
Sorry, my bad.
Because you have a function of x, right? X is the input variable. We are integrating that function with respect to x. X is the independent variable of the function. N is only to help us with the notation of the infinite series. You don't get to choose x. I mean, sorry, you don't get to choose n. Okay. N is fixed. It's counting through, right? You don't get to change it. You can't tell me, hey, I want n to be 5. Now what happens? It's n has to go from 0 to infinity. So in that sense, it's not variable. It has to follow a certain pattern, where the x you plug in can be any number in the interval of convergence. That's variable. That you can provide me anything you want in that interval. Okay, I've got to proceed. Not discrediting your questions. These are good conversations, but obviously, this is where I think about, like, if we were sitting out on a bench out in outside on campus, we could have these conversations. Like that's the way they used to learn, right? You have this idea of a classroom. It used to just be a bunch of people sitting outside talking shit to each other. Like, what do you think? Oh, I think this. I mean, that's where learning really takes place, and that's how learning takes place, is when you sit there and have dialogue like that. It's just, unfortunately, we have to keep the train on the tracks here, or else we'll go way off.
No,
right?
no, you're so good. I should have asked you later. That's my fault.
No, it's good. I mean, it's all right.
So
Okay,
you
so
do
when
see
we
my
get-
confusion, right? I just want to, like,
I think
it's
I
not
do.
simple. It's not like a simple, oh no, that's okay. Never mind.
Yeah,
never mind.
it's variables are an abstract idea. So, I want to be as precise as possible with my response to you without just being agreeable. All right, so when we take the derivative of a power series, we just bring the n down, subtract 1, shift the index. When we do the antiderivative of a series, we do a c plus, and then nothing changes in the index, and then we just use the good old power rule. We add 1 to the exponent, and we divide by n plus 1. So just like we did earlier this semester when we learned power rule. So with that knowledge, let's first do this example where we're going to find the derivative of this Bessel function that we had talked about before. Do you remember this Bessel function? We did this in class where I asked for whether or not this converged or diverged. Shall we go back and look and see where it was? I don't even remember where it was. I think it would have been under ratio test. No, I've gone too far. Wasn't last time, was it? I know we did it. Does it look familiar or no?
I recognize it. I don't remember
Okay,
when we
yeah,
did it,
I'm
but I
not gonna
remember
go.
doing it.
All right, so the instructions here are for us to find the derivative, right? So we want to find J prime, or J sub 0 prime of X. All right, well, that's pretty nasty looking, right? I mean, that's pretty nasty. So what I'm going to do first is I'm going to write this series out. I'm going to write a few terms out. So let's let n be 0 to start. If n is 0, I get a positive 1. X to the 0 is 1. So the top is 1. The bottom is 2 to the second power. I'm not going to write 4. And then I'm going to get 0 factorial squared, right? That's what I get there. Oh, I forgot the x. And then x to the 0 power. Yeah, I'm going to write the x there. Right, that's what we get if we plug in 0. With me? Oh, wait, hold on. That's 2 to the 0 on the bottom. I apologize. 2 to the 0. Plus, now let's let n be 1. If n is 1, we're going to get a negative. So let's make it minus instead. If n is 1 there, I get x squared on top. And then on the bottom, I get, let's see, if n is 1, there's my 2 squared. And then there's my 1 factorial squared. Next one's going to be positive, right? Because I'm plugging in 2 for n now. So I get positive x to what power? We're at 4, right? X to the 4th. Over 2 to the 4th, 2 factorial squared. Let's do 2 more. Minus this time, x to the 6th over 2 to the 6th times, where are we at? We're plugging in 3, right? So 3 factorial squared. One more, plus x to the 8th, 2 to the 8th, 4 factorial squared, and the next one will be minus, but I'm going to put plus there. All right, that's me writing out the first few terms. The reason I did that is just to help you see what the derivative is going to be. So if I take the derivative now, right? What is the derivative of this? Constant, constant, constant. X to the 0 is 1. This is all constants, right? Derivative constant 0. Okay, now, how about this one right here? The only thing that's going to get a derivative is the x squared. Everything else is constants. So you can just bring them for the ride. They just come along. So the 2 comes out, right? That's it. So minus 2x over 2 squared times 1 factorial squared. I realize I could cancel 2s. I'm not going to. I'm trying to see a pattern. Plus now 4x cubed. And then over 2 to the 4th, 2 factorial squared. Same thing. 6 comes out. So minus 6x to the 5th over 2 to the 6th, 3 factorial squared. One more. 8x to the 7th over 2 to the 8th, 4 factorial squared. That looked like I did everything okay there. I wrote out the first few terms and then I differentiated. This is what the derivative should look like. So go back to this real quick. Go back here. And I want us to write that original Bessel function, not the derivative. I want us to write it out like this. I want us to isolate the x part. Right, so all I did there is I just peeled that x to the 2n off to the side. Everything else, right, is like the c sub n. It's just something that keeps changing, but it's just a number. And so I guess what I'm asking you to do is to tell me, like, if you were to take the derivative using like the good old fashioned power rule without doing all this stuff, would we get the same answer? So let's take the derivative. Let's what we'd have to shift the index up to 1, because we do that when we take derivatives of power series. And then everything that's c sub n, let's leave it. Constants come for the ride. And then on the x to the 2n, let's just do that the way we would do that in Cal 1. Bring the 2n out front. X to the what power?
2n minus 1.
2n minus 1. Subtract 1 from the power. Does it work? Is that what this is? How would we check it? Start plugging in
Plug
numbers,
values
right?
in. Yeah.
Let's see, if we plug in 1, we'll get a negative, right? Okay, good. This first term's negative. If we plug in 1 here, we get 2 squared. We get 1 factorial squared. Okay, great. How about this? 2n x to the what? Is it working or
1.
not?
Yeah, it's just x to the 1.
This is x to the 1. So if I plug in 1, right? If I plug in 1 into this, this is exactly what I get when n is 1. What about this next one? Is this what I get when I plug in n is 2 into my formula down here? I'll be positive, right? 2 to the 4th power. Yes, I've got 2 to the 4th. 2 factorial squared. Yes, I have that. 2 times 2, that's 4. And then x to the 4 minus 1 is 3. Yeah, that works.
Yeah. So
Yeah, go ahead.
oh, I was just gonna say, so that you can do that. If you can work out that, hey, that's all gonna be a constant, you can pull that out and then just take your power rule of your x.
Exactly. That's the point of this example, is to show you, look, there's 2 ways we could do this. We could write out all the terms and then just differentiate them. Or we could isolate the part that's the x to the 2n from everything else that's just a number, and then use our power rule from Cal 1.
That way.
That's
I like that way.
easier, right? But sometimes this is actually easier, because sometimes this formula is really bad. So stay tuned. All
That's
right,
badass.
let's move on. I really want to get this example in before the day is up. All right, so recap what we've done today. We started out, recap what we've done today. For this section, I said, hey, everyone remember this, right? I gave you an example, said, hey, rewrite this as a power series. And then we were able to like say, oh, this kind of looks like this, and we rewrote it, right? And we were able to make it look like 1 over 1 minus u. And then the next example, it was a little bit harder. I had to rewrite x to the 4th over x plus 5, and I had to somehow tweak shit up and then pull this out and then get the series from this with a little interval convergence, and then push this back in, and then I was able to do it, right? But again, it came down to making it look like 1 over 1 minus u. And then we got to this where I talked about derivatives and integrals. So it seems like we've shifted gears and we're doing something different now, right? Well, I want us to go back, and I want us to actually try another problem, all right? I want us to try this problem. I want us to try and convert that to a power series. So when you look at that, remember the thing that we have burned in from the beginning of class is this: if we can make it look like this, right, then we're like happy, because if we can make it look like 1/1 minus u, we know a power series for that. Yeah. So you look at this and you're like, well, I got this, man. This is just 1/1 minus x times 1/1 minus x. Yeah. Isn't that what that is? If I multiply across, right, just multiply straight across. 1 times 1 is that. 1 minus x times 1 minus x is 1 minus x squared. So this is this, right? But we run into a major problem because, yes, I agree with you. This would turn into a series, okay? This would be the series sum n equals 0 to infinity of x to the n. Why? I'm using this formula, right? And then it would be times another series, n equals 0 to infinity of x to the n again. And the problem with this is that you cannot figure out what that is as a single series. The product of two infinite series is not easy to represent as a single series. These are two series multiplied together. And what we're looking for is a power series, which is a single series. You understand what I'm saying here? This is two series together multiplied. I want a single series as an answer. Because
why can't it?
Well, let me show you. Look, this right here, okay, is 1 plus x squared plus x cubed forever. Agreed? Okay, times the same thing. 1 plus x squared plus x cubed forever. Yeah, that's true. I'm not saying that that's not true, but this doesn't help us. Because what if I ask you to take the derivative now? Okay, imagine I ask you to take the derivative of this. There's a problem. You have a product. You can't just do each one by one, right? There's a
product rule.
Exactly. And so you don't have the fortune of just saying, oh, if I want the derivative of this, I'll just take derivative of each one of those separately. Nope, cannot do that. So it's not helpful to us. If we had a single series, then we can differentiate and integrate piece by piece because it's just a bunch of things added up. Does that make sense? It's not that we can't do it, it's just that it's not useful.
So would we then multiply our bottom across itself so that we get 1 minus 2x plus x squared?
Well, actually, what we're going to do, Hunter, I would never expect anyone to see. So it's going to kind of blow your mind the first time you see it. All right.
I thought I had it for a second. I was looking at it and I went, I see something dumb I can do, but okay.
Yeah. So first thing we have to realize is that we can't do this. Can't do this. Not helpful, right? Can't do this. Not useful. Not useful for what we're trying to accomplish, which is to get one single series. All right, so let me start from scratch here. 1 over 1 minus x, that quantity squared. I sit there and I start thinking about this, right? And I go to myself, wait a minute, hold on a second, hold on, right? Say, wait a minute, wait. If I take 1 over 1 minus x, right? That's the one that we do know about, right? The problem is the squared here. We don't have that. But if I look at this and I ask you right now to take the derivative of it, what would the derivative of that be? So instead of doing that, take the derivative of 1 minus x to the negative 1. Aren't those the same thing? So take the derivative of this. The negative 1 comes out. 1 minus x to the negative 2 times negative 1. And that's just chain rule, right? Negative 1 comes out, this to the negative 2. But whoa, wait, whoa, what is that?
It's 1 over 1 minus x squared.
That's that. That's that, right? Yes,
Oh,
yes.
no.
So I've noticed that. I've noticed that. That this right here is the derivative of this. Okay, so I'm going to write this down. I'm going to say 1 minus 1, or sorry, 1 over 1 minus x squared is equal to the derivative, right, of 1 over 1 minus x. Do you all agree with that statement?
Yes.
But that is equal to the derivative of the sum n equals 0 to infinity of x to the n, because I can turn this into that series so long as the absolute value of x is less than 1. So what I'm looking for, I'm trying to find the series. I'm trying to find the series for that, right? What's the series for this, everyone? No idea. Oh, wait, I recognize this. Yeah, you don't recognize that. Now that you've seen it, you know that we can start looking down that alley, all right? I noticed that this is the derivative of this. Holy crap. Okay, so this equals the derivative of that, but that's equal to this. And we just learned this. We know what this is. This is the sum. N equals 1, right? I'm going to shift the index, and I'm going to use the good old power rule, x to the n minus 1. And then that, if I wanted to write out the few first terms, would be 1 plus 2x plus 3x squared plus 4x cubed plus dot, dot, dot forever. That is the power series of that. I had to recognize that this is the derivative of this. Rewrote it as its series, took its derivative, and then that must be what that is then. I'm going to go back over here. I'm going to just show you 1 over 1 minus x squared. Let's look at the series for this. Come on, hurry up. 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4. There it is.
So I hate to ask this question, but does it work if it's if the thing we got is the integral of another that we know?
Funny you should ask.
Yeah, I kind of expected that.
Funny you should ask. Express this as a power series.
Wait, Professor.
Yes.
There's other rules as opposed to 1 over 1 minus u. What, if you don't mind me asking, why are we moving it so much to where it fits that as opposed to learning other rules? Does it make sense? I don't know if I'm.
Well, 1 over 1 minus u is like the
ultimate.
The first one we use, geometric series. It comes from geometric series, and it's just to illustrate how we can take things that we've seen and turn them into that. But the next section, we get the Taylor formula and how we can do this for pretty much any function. So we will have the powerful method next class.
We have to learn to acquire that power. I got you.
Well, what you don't want to do is be sitting in a physics class and see them do this. And let me see, what would this turn into? So I'm going to have to think this through. This right here is the same as 1 over 1 minus negative x cubed, right? That's what that is. And then that becomes some negative x cubed in here to the n equals 0 to infinity. So you're sitting there and you're reading a physics book, and all of a sudden they say, you know what, 1 over 1 plus x cubed, we're going to approximate that with, let's see, if n is 0, you get 1 minus x cubed, and then plus x to the 6th minus x to the 9th. You don't want to be sitting in some class or engineering class going, how in the hell is this, right? You want to understand that they're using this, because this happens quite a bit, where they take something and approximate it with something. You're like, where'd that come from? I'll show you a video. You know what? Yeah, no, I'll show it to you later. There's a video, a pretty famous video, at least in my mind, of a teacher pretty much getting ripped apart by his students because he's going from one line to another on the board, and the students are telling him that the math he's doing doesn't make any sense. And everything he's doing is correct, but the students don't understand like this. Like, they just don't understand it. They didn't learn it, I guess. But they're telling him he's wrong, which isn't right. I mean, this is correct. This is actually equal to this, exactly equal to that forever, as long as the absolute value of x is less than 1. So we learn it because it's useful, comes up later. Okay, this right here. Here, how in the world, because the only tool we have today is this, right? How in the world are we going to get it to this?
Take the integral.
Okay.
We recognize that this is the integral of that.
Is it, so what is the integral? The integral of what though?
1 over 1 minus x. 1
How about
plus
this?
x,
I think
actually.
it's 1 over 1 plus x, right?
Yeah. Yeah.
The antiderivative of that. So I'm looking at this and I'm realizing the antiderivative of that is equal to the natural log of 1 plus x plus some constant, right? Y'all buy that? So that's what I know, right? I know that the natural log, the thing I'm trying to find the power series of, is equal to the integral of 1 over 1 plus x dx. But I can rewrite 1 over 1 plus x as 1 over 1 minus negative x dx, can't I? And then that I can turn into, right, this in here, I can turn into its series. This is the series sum n equals 0 to infinity of negative x to the n. If the absolute value of x is less than 1, right? Then I can do this to this. And we just learned how to do antiderivatives of series. So I don't actually have to write it all out. I can just give you the answer right now. It's the sum. Index does not change on an antiderivative, but I just use the power rule on this, right? That's all I do. One thing we should do here, just to be safe so we know, that's negative 1 to the n, x to the n, right? Let me rewrite it that way. Negative 1 to the n, x to the n. Because we want an x to the n, we don't want the negative x to the n. So I'm going to split it apart here. And then our antiderivative will be the negative 1 to the n, x to the n plus 1 over n plus 1. I'm almost out of time. That's our answer, but let's get a few of these. If we plug in 0, we get a positive number. We get x on top and 1 on the bottom. We plug in 1, we get a negative number, and we get x squared over 2. And then plus, I think it's going to be pretty easy to pick up this pattern. X minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. Gonna check it. Well, I'm gonna verify it. I want to do series log of 1 plus x. Right there.
What is
All
the O in the Wolfram? I saw that it had like uppercase O x7. What is that for?
Well, that's what we were talking about earlier. This is just telling you that, you know what, we're
Oof.
stopping at the order, the 7th order, that this actually goes forever.
Sorry, I think I got distracted at that point. My bad.
No, it's okay. I think you might be able to say here, series order 10. Let me see if it'll do it. Yeah, see? I don't know why I went to 12. That's weird. I put 10. Oh, X to the 10th. No, why did it give us 11? That's weird. Okay. It just really means it goes forever. It's only showing you the first part. Let me see what these other examples are. Why don't you try those on your own? These are the last two examples, I believe, of the section. So we're pretty much, we got through this today. See how those go. All right, that's it, right? Have a good weekend. Is that where we are?
I checked the schedule just like a second ago. I think that's when I got distracted. We only have 1 day needed, like quotations needed to do the Taylor and McLaurin. And if we're done with that, are we gonna do like maybe trying to touch Polar and on?
No way we're doing
No.
Taylor and McLaurin in 1 day. There's
Okay, no way.
there's
Okay.
no way. It's gonna be 2. Yeah, because there's also, we're supposed to somehow get in there multiplication. What is it? Multiplication, division. Oh, no, it's in that section. Yeah, I mean, 8.7, if you were to ask me at the beginning of the semester, like, what is the absolute section I want to get to? It's 8.7. Because 8.7 is where we actually give you the big formula. Like, we've been working on series this whole time to be able to see how in the world you can come up with a power series for e to the x. Like, what's the power series for e to the x? How do you generate it? And then next week, I'm actually going to show you all this. Y'all can go if you need to. I'm actually going to show you all the proof of this formula that you probably have seen at some point in your life, this equation. You may have seen that. It's told, people argue that that's the most beautiful equation in math. I'm not saying it is, but I will prove that's true. And I'll need a series to do it, but I got to build some stuff up first before I can do that.
Question, are we good to do all the math for 8.6 or?
I think
Homework?
there might be some struggles because there's one, let me see what the homework section is. Let me just give you the one problem to avoid, like just know it's going to be, let me see, it's going to be bad, 3,474. Okay, so number 13 in 8.6 is, they try and take you step by step through it, see how it goes. But the thing is, like problem number 20, kind of requires that you did number 13. So I would say 13 and 20 are kind of tough. Let me see, what does this say to do? 3 through 20? Yeah. Other than that, 13 and 20, I think other than that, those others are all within 11 and 12, you have to do partial fraction decomposition first. So skip 11 and 12. Yeah. So 1 through 20, except no 11, no 12, no 13, no 20. All the others should be at least within reach. All right, I'm gonna head to my office hours because I have some students that are supposed to meet me in there. Y'all have a good one.
Sure. Have a nice,
Great
nice
weekend.
weekend.
Too.